Hello, welcome to a new section of the course, Cogs and Pulleys, Building Blocks. Data structures don't have any use without algorithms to manipulate them, and algorithms cannot work without data structures. Some of the most common ways of storing a collection of values have their own names. We will discuss them in this section. They are arrays, linked lists, doubly linked lists, and circular linked lists. Now we move on to the first video of this section that deals with arrays. In this video, we're going to insert elements in an array from the array and outside of the array. We will also append elements to it. If you are a Java programmer, you must have worked with arrays. Arrays are the basic storage mechanisms available for a sequence of data. The best thing about arrays is that the elements of an array are co-located sequentially and can be accessed completely and randomly with single instructions. For implementing an array, let's create a class array. The traversal of an array element by an element is very simple. Since any element can be accessed randomly, you just keep incrementing an index and keep accessing the element at this index. Let's write a code that shows both traversal and random access in an array. Here it is. Here we will insert elements in an array. All the elements in an array are stored in contiguous memory. This makes it possible to access any element in a constant amount of time. A program simply needs to compute the offset that corresponds to an index, and it reads the information directly. But this means that they are also limited and have a fixed size. If you want to insert a new element into an array, you will need to create a new array with one or more elements and copy the entire data from the original data along with the new value. To avoid all this complexity, we will start with moving an existing element to a new position. What we are looking to do is to take an element out, shift all the elements up to the target position to make space in this position, and insert the value we extracted in the same place. The figure here explains what we mean by this operation. The thin black arrows show the movement of the element that is being reinserted, and the thick white arrow shows the shift of the elements of the array. In each case, the bottom figure shows the array after the reinsertion is done. Notice that the shifting is done either to the left or right, depending on what the start and the end index are. Let's put this in code. What would be the running time complexity of the preceding algorithm? For all our cases, we will only consider the worst case. When does an algorithm perform worst? To understand this, let's see what the most frequent operation in an algorithm is. It is, of course, the shift that happens in the loop. The number of shifts become maximum when start index is at the beginning of the array and target index at the end, or vice versa. This is when all but one element has to be shifted one by one. The running time in this case must be some constant times the number of elements of the array, plus some other constant to account for the non-repeating operations. So it is T of n equals K of n minus 1 plus C for some constants K and C, where n is the number of elements in the array and T of n is the running time of the algorithm. It is expressed like this. Now I will explain it. As per Rule 1 of the definition of big O, T of n is equal to O of Kn plus C minus K. As per Rule 3, T of n is equal to O of Kn. We know that mod of minus C minus K is less than mod of Kn plus C minus K is true for sufficiently large n. Therefore, as per Rule 3, since T of n equals to O of Kn plus C minus K, it means T of n is O of Kn plus C minus K plus minus C minus K. That is, T of n is O Kn. And finally, as per Rule 2, T of n equals O of n. Now, since the array is the major input in the algorithm, the size of the input is represented by n. So we will say the running time of the algorithm is O of n, where n is the size of the input. Now we will look at insertion of a new element and the process of appending it. Since arrays are fixed in size, insertion requires us to create a new array and copy all the earlier elements into it. The figure here explains the idea of an insertion made in a new array. Implement the method insert extra element at index. First, you copy all the elements before the targeted position as they are in the original array. Then the new value must be put in the correct position. In the end, copy the rest of the elements in the array by shifting their position by 1. The for loop here does that, and then we will return the new array. When we have the code ready, appending it would mean just inserting it at the end, using append element as shown in the code. Now implement the main method. Here we have created an array, inserted element at index 5 into index 2, inserted extra element at index 5 with the value -1. And lastly, we append the element 5000 to our array. Let's run the program. Here you can see the different outputs for the different methods. What is the running time complexity of the preceding algorithm? Well, no matter what we do, we must copy all the elements of the original array to the new array, and this is the operation in the loop. So the running time is Tn equals Kn plus C for some constants k and c, and n is the size of the array, which is the size of the input. Great! In this video, we inserted elements into arrays in different ways.